and also derive, well, we're going to use this idea in solving 4 different problems that we haven't talked about yet. One we've sort of talked about, another we haven't. And so the first thing we're going to do is do 4 additional examples, and each one of those will be a candidate type of a problem for the exam. And in the second half of the class, I'll work out 8 additional problems that or present them that are candidates. I'll only have about maybe 9 or 10 on the test, that I'll present about 12. And there might be one that's unknown, but it's going to be similar to these, that it's not going to be like, where did that come from? We have to solve a quantum field theory problem in the color force, and we never talked about that. Then that's not going to happen. Okay, so the first example I want to do is, let's say we have an object, and we'll give it a mass. I like to use things that are easy to calculate with, because the calculations themselves, the numbers are less important in the process. And let's say it has an initial velocity, let's just say we'll make it 5 meters per second. And we know that in use of K here, the coefficient of kinetic friction is 0.2. It's a flat surface. It's going ahead with this velocity. There's no applied force, so we're not giving any additional energy to it. We're also not taking away its energy, and in that sense, the braking force is taking away energy, but it's still doing work on the object. But that's the tricky thing about saying positive and negative work, because you can have an accelerating force and a force that slows it down, and they're both doing work on the object, but they would say one's doing negative work because it's taking energy away from it. And that just seems convoluted, and what is negative work? It's like saying a negative distance or something. And so I don't even deal with that. I just, I mean, it's doable, but it's just an extra step that why, why? Okay, so no applied force here. And what we're going to ask is, how far does this go before stopping? We have kinetic energy. Okay, so here what we're doing is, when an object is already moving, the force of kinetic friction is going to work to oppose it. And so it's going to have to overcome, with its own energy, it's going to have to overcome that force of kinetic friction. So here the kinetic energy initial, and that's going to be the initial kinetic energy of the mass, is used to overcome friction. So we start off with a certain amount of energy, and it's going to vanish. It's going to still be kinetic energy, but it's going to be kinetic energy in the road that it's going on, or whatever the surface is. But it's used to overcome friction. And so only as long as we have enough kinetic energy to overcome the frictional force can we keep moving. So in other words, the kinetic energy initial, it's going to go into overcoming the frictional force. So that's going to be the energy lost to friction. It's going to be equal to that in the final stand. And what's valuable about knowing the energy lost to friction is that it's going to be the force of kinetic friction times the distance it travels. And this is what we need. We need the distance it travels. It's a constant force that this isn't so much the force of kinetic friction. It's a force that this moving object, it's applied against it, but it's equal in magnitude to the force of kinetic friction, because the force that opposes it is going this way, and we're applying it all that way. So in a sense, it's an applied force from the interaction of the mass with whatever it is that it's sliding on, but its magnitude is equal to the force of kinetic friction, so that's why we write it that way. And so, and remember that this distance is the distance you move in the direction of the force that we're looking at how much energy it gives, and the force is going in that direction directly opposing the force of kinetic friction. It's going to move at a certain distance until we run out of kinetic energy. So that's going to be how we get the distance. So all we have to do with this is solve this. We had from last time an equation for this F sub k, and it was the force, well, it looked like this. In the final analysis, we used the form that looks like this. This was the slope of the angle. It's 0 degrees here because it's not a sloped surface. So this collectively is otherwise known as 1. So it's just going to be the coefficient of kinetic friction times mass times gravity. We'll use here the fiction that this is 10 meters per second squared. It's not, but it's close enough, so we'll make our life easier. We'll use the mass that's given, which is 2, also easy to calculate with, and then we have 0.2 for u sub k. So that's going to be, what, 4. So the force of kinetic friction, that is the force that's required to keep it moving at a constant rate, we have to apply 4 newtons the entire time it's moving. And it's going to be moving the entire time before it comes to a stop. And the energy to apply that force comes from the kinetic energy. So now we have the initial kinetic energy, so that leads us to the initial kinetic energy, which is equal to mv initial squared over 2. That's equal to the force of kinetic friction times the distance, so it's equal to 4 times the distance. Well, we can start putting we know all the other parameters. We know that the mass is 2, and so 2 divided by 2, that thing's gone. 5, we're going to square that, so you get 5 squared is equal to 4 times d. So we have 25. And then that looks like a mathematical fiction. 25 is equal to 40, if you say it that way. What? Okay, so 25 divided out by 4, we're going to get about 6, we're going to get, not about, exactly 6.25. Yeah, 6.25 meters is the distance this thing has moved. And again, we looked at what happened to the energy. At the beginning it had kinetic energy. It was used to oppose this force of kinetic friction that was opposing its motion, and it moved as long as its energy held out. And then when it ran out, it comes to a stop. Everybody goes home, game over, season finished. Okay, so questions about this example here. It's one that you should be familiar with, so that if I ask this one, it'll be really asked just like this. How far does it go before stopping? We can ask other questions about it. We could ask, how long does it take to get there? That would be another possibility. How long does it take to get there? If I did a small variation on it, how long does it take to get there? And how do we do that one? Well, we know it's slowing down. If we ask how long it took to get there, I'm not going to ask how long it takes to get there. It's a good question, that unless that's a mystery question, which I don't know what the mystery question is going to be, but I'm not going to talk about it except for saying, hey, that might be the mystery question. At most, I'll have one mystery question, maybe not even that. But if you can do this one, you'll be in good shape, because it's going to be, it might be one of the 9 or 10 on the test. Again, we'll have 12 problems that I show you like this that are candidates. 9 or 10, 8 or 9 of those will be on the test with possibly one unknown question. Okay, so example 2, it's going to be similar. Exactly the same in every possible and conceivable way, including ways that are not conceivable, yet completely different. Now, it's going to be very, very similar. We're going to have the same situation, except that now this object is at the bottom of a slope. We have a mass. It's going to be going up. Again, we're going to have 5 meters per second as its initial velocity, but it's a velocity straight up the slope. We'll again have the same, we'll do every value the same to make the calculations easier, except we're going to have to add an angle for the slope here, and we'll give it a 30-degree angle. That's often easy to calculate because what sine of 30 is like 1/2 or something. like 0.866 or something for the sine, for the cosine, and so it makes the calculations easier. I may have gotten those reversed, but I think I have them. Okay, so, and it's going to be the same question. The question is, we know it goes up the slope, but the question is, how far does it go up the slope? That's going to be a bit trickier question. We can do it here, but now we're battling two different forces on the way up. Again, and so again, the question is, how far does it go up the slope? And so again, if we look at the energy, our initial energy, it's all kinetic energy at the bottom. It's going to gain potential energy at the end. It doesn't have anything because here we've always been having the ground as h is equal to 0. When we have, remember the formula for potential energy against gravity was mgh, and so we count the flat surface as h is equal to 0. So it starts off with no potential energy. It's all kinetic energy. And we're going to lose some energy to friction. So we're going to have to take both these things into account. We can once again very quickly get our initial kinetic energy. Again, this is just m v initial squared over 2. And again, we're looking at what happens to it. It's going to work to push against the gravitational force and against friction, and then when it runs out of energy, it's going to stop. It should go less than 6.25 meters because now it's battling two forces. Pushing down on it that it has to work against is the force of kinetic friction, but there's also that Fg x prime force we identified before. It's working against that now too. So this is going to be mgh final is one way of doing it. Remember, the potential energy is the work that it does, or the energy used to work against gravity. Or in this case, it's also going to be equal to Fgx times the distance. Those will give the same thing because now the only component of the gravitational force, and that should be x prime. This is the only component of gravity it works against. So in a sense, we have an applied force from the object, and it's applying this kinetic energy to overcoming gravity and to overcoming friction. And again, this will just be our force of kinetic friction times the distance. So we have two things that involve the distance. So two forces worked against by the kinetic energy initial. The kinetic energy initial, as it's slowing down, is applying a force that exactly matches these two. So again, in a sense, we can think of it as the forces acting on the system is that in one direction we have F sub k, and we have Fgx prime. Going against it is an applied force, and again, this is due to the decreasing initial kinetic energy. So you have, and they exactly oppose each other, and that's why we can calculate this as the sum of these two, because in magnitude it's equal to those two. And so again, as I've said before, that a lot of the story in physics is to follow what happens to the energy. They do that in high energy physics, the particle colliders, and it's very helpful in introductory classes like this too. And this is a pretty involved problem here. Introductory, yeah, but it's still pretty involved. Okay, so to get what we're looking for, we just need the distance. So we can use this thing over here that we set up over here. If we call that equation 1, equation 1 implies that, again, we have mv initial squared over 2 is equal to fg x prime times the distance plus f sub k times the distance. And since we need the distance, we can factor it out. We have this in parentheses times the distance, and now all we have to do is divide one side by the other. Well, not one side by the other, but divide in parentheses, what's in parentheses, divide both sides by that, and we get mv initial squared over 2 divided by fgx prime plus f sub k. That's going to be our distance. Physically, we know that it's going to not go as high because now it's battling two forces. So if we get more than 6.25 meters, we know something's wrong with our setup, or we made a small calculation error somewhere. And so barring that, we should get an answer that makes good physical sense as well. So let's start putting things in. We have mv initial squared over 2, and then this force is just, we said mg, in this case it was going to be sine of the angle, plus, with the other one, again, this is our, in the tilted coordinate system, that was the component of gravity that's going down the slope that this thing is battling against. And we have mu sub k, again, mg cosine of the angle, and that's what things come out to be in this case. Again, this is f sub k, and all that's equal to the distance. We can simplify this further. We can pull out an mg on the bottom, and we'll do that. There are many ways of solving this at this point, but we'll just do a little more algebra and simplify this more. So we'll pull out the 2 mg and end up having sine of the angle plus mu sub k cosine of the angle. That's equal to the distance. And then we can cancel the mass, and we end up with an expression that now we can just put everything that we know into it, and we'll have a distance. And again, we can check against our first answer. It should go less up the slope because it's that the energy is being used to battle two forces rather than one. But then again, at the same time, the force of kinetic friction has decreased as well. So will it go up further? I'm not sure, actually. Thinking about it more, because f sub k is going to decrease because now it's at an angle. We'll see if those effects balance each other out and we get the same result. But notice over here, the mass doesn't come into play with this. That there's no effect of the mass. And it was the same way in the first example. There was no effect from the mass because that was canceled out. Well, no, it wasn't canceled out of hand. It was just, well, we could have divided through and canceled out the mass, and it would have, but we need to look at that part. Okay, so v squared. So again, we have d is equal to 5 squared, and that again is the initial velocity squared. And we have 2 in case somebody doesn't realize, hey, 1 plus 1. I gave that as a bonus question one time on a quiz about 7 years ago, and everybody was looking for the trick I was trying to have. Some people said, okay, 1 plus 1, that's 11. Some people did binary code on it. Half the class refused to answer. I don't know what she's looking for, but they made it more complex. It's easy in physics to make it more complex than it has to be. Okay, so sine of the angle. So we have sine, and we're given an angle that I gave us of 30 degrees plus mu sub k, which is still 0.2, times the cosine of 30 degrees. And that's going to give us a distance, and whether it comes out ahead or behind, I really don't know at this point. It's going to be interesting to see if the effects of the decreased, okay, so this is 0.5 plus 0.2 times about 0.867. So we have 0.5 plus about 0.1734. It's always nice to see like 17 goes into 34 twice, 17's prime, and stuff like that jumps out sometimes. Well, a lot really, depending on what your affinity for enjoying mathematics is. Okay, so now we have and it's all over 5 squared. Sorry, this got to be a little bit, I'll rewrite it here. Okay, so we have D is equal to 5 squared. It's not going to be so crowded here, so it's 2 times 10, plus add that together, that's 0.6734. And I think it's going to be less. Oh yeah, it's only 1.85 or 1.86. So it goes up dramatically less because now it's battling, oh, in fact, yeah, okay, so about 1.86 meters. So that's the distance it goes up the slope. Okay, other than this kind of crowd over here, most of it should be, you can follow along with it, but are there questions about it? So this is the second type of a question that may appear on the test.
We're getting the formula sheet on.
Oh, yeah. For the formula sheet, what I'll have is, like for this one, what I would have in the formula sheet for you, I would have things like FG x prime is equal to mg sine of the angle. I'll have that. I would have something like, I'd have kinetic energy is equal to mv squared over 2. I'd have potential energy is equal to mgh. And maybe even, yeah, like this fgx d, and the work to overcome friction is equal to f sub k times d. And then we have f sub k is equal to, so all of this, this is what you would see on your formula sheet that if you knew what to do with it, well, then you have it right there, you know. So I'll have, that's what it's going to look like on the formula sheet, so you'll have that at your disposal. Any question where it's, that I'm bringing up here, that there's a question of what you're going to have to refer back to, I'll tell you if you ask it for that question, what we're going to have to see. Okay, so those are 2 of the questions. There were 2 other examples I wanted to give. Each one's a little bit involved, so we're going to have enough time to finish them before we go upstairs. Then we'll go upstairs, I'll answer questions about homework, and I'll show you the other 8 questions. But they won't take as long to go through these because they're questions we've already done before, and I'll just present them to you again and kind of show some streamlined solution ideas to take care of them. So these 4 are taking a bit longer, but that's because they're really new to the class here. So a third example, it's similar to one that we've done before, but it has an important difference as well. So we have an applied force. It's applied. We have an acceleration. I'll give you an acceleration, and we'll say 3 meters per second squared. We'll have an initial velocity of 0. We'll have a mass of 2 kilograms. We'll have a mu sub k value of 0.2. And the last thing we have is F sub A is applied for 3 seconds. And this one has a few more things I want to ask about. How far does it go? And I'm asking this one first because it's going to help us get the other ones. On the test, I might not ask how far does it go to kind of prompt you along, but I'm doing it right here to, because we're going to need it for the next thing we do. Then we'll ask, okay, what is FA? And then, what is the energy supplied by the applied force? And then we'll find, we'll also find the kinetic energy final, and and the energy used to overcome friction that we've called W sub F before. Find those two, and then finally, we'll say find the average power. And I'll introduce the idea of power when we get to this question. It's not difficult, really, at least not the very basic idea of it is. It's the amount of energy you supply per unit of time. And so I'll spell that out when we get to it. Okay, so this one's a little bit different. That how far does this thing go? Well, we again have an we again have an exposition equation, and it has again this form we've seen about 17 billion times, well, 17 billion and 500, and I lose count, but okay, so we've seen it so frequently, and it's useful in second year physics and really in fundamental physics research. It's a very useful equation, and we're going to say it starts off at the zero position. We know its velocity is zero, and by the way, whenever we set the initial position equal to zero, when we find how far it goes, we find its position at a certain time, that's also how far it is. We don't have to take away the distance from the origin to find out how far it goes. Okay, and then we have...
Quick question, real fast.
Oh, yeah.
How do you know when to use like this formula or something like, how would you, I'm kind of confused on it, like, how do you know which formula to apply to which question?
Say, as opposed to say something like this.
What we did earlier.
Yeah.
With the distance and force.
Okay, okay. Let's look at what happened that if we tried to apply those.
Is it because you gave us an acceleration, that's what we're using?
And I also gave you a time that it's applied, and I'm asking how far it goes. And the only questions that we have a distance in them, kinetic energy doesn't give that to us. The only equations like that are this x of t equation and this vf squared is equal to v initial squared plus 2ax. And we need this. At this point, we don't know what that one is. I mean, that's a good question. And so what you can think about is, okay, what do we have in it, equations that have what we need to find in it? And really there are just two of them, this one and this one here. We know that's zero. We know this. But that leaves us with two unknowns for one equation. We can get this, and so this is the second route we can go. So we'll look at a second way of getting it. The best answer for that question is look at what you're trying to find and see what equations have that. So we'll solve it this way first, then we'll look at the second equation. Because, as I said, there are so often two or more ways of solving the problem, and this is just one of them for this case. Okay, so we have 3 here. So x of t is equal to 3/2 t squared. So x at 3, that's how far it moves. So it's 3/2 since it goes, it's applied for 3 seconds. And so we have 3 times 9/2. So 27/2, or 13.5 meters. We have the distance that it goes. That's one method of getting it. The other method of getting it again is it involves more work, but we can do it. So method 2, we have vf squared is equal to v initial squared plus 2ax. We need the x. A is given as 3, and that should be squared. This is given as 0. We need this. That we also know a velocity equation. We know vt is equal to v0 plus at. We know its initial velocity is 0. We know this is 3. So v at time 3 is its final velocity. Well, let's first get the velocity equation here. So vt is equal to 3t. So we have v at time 3 is equal to 3 times 3, or 9. We can go put that up here, and we should get the same number. So we take that over here, and we apply it over here, so we have 9 squared is equal to 2 times 3 times x. So we have 81 on this side, and we have 6x. So we should have 81 over 6 is equal to x. 6 times 13 is 78, and that leaves 3 extra. So we have 13 and 3 6, or 13.5. And we get the same number, but we had to go through a few extra steps over here to get there. How do you know which way is faster to go? Well, you probably won't. Yeah.
On the last equation that we did, we can use the same distance formula.
Same distance formula, which
The
distance formula?
MPI squared over 2 divided by FGX 1 plus FK. Like, we couldn't do that one for this one, because I think that's what the question they were
Oh,
asking.
I see, okay, let's see what happens if we do that. The last one, we also had gravity involved. Okay, so, in other words, okay, let's look at if we try to do that. We have, in this case, that there is no initial kinetic energy, it's only an applied force.
Okay.
So in other words, what we're gonna have is, a good question, now I understand what you're talking about. We can't use that because we don't have any initial kinetic energy to equate it to. It's coming from the applied force, and to determine the amount of energy the applied force gives it, we have to know how far it goes first.
Okay.
Okay, so that's the answer to the question, I think in the full detail that anybody was asking about. Okay, again, you don't have a way of knowing which one is faster. I like this one because it's faster, but sometimes I'll be doing something a certain way and someone says, hey, how about this way? Oh yeah, that's better, let's do it that way. And because sometimes there are 2, 3, 4, 5 ways of approaching the same problem. And there may be another way for this one. I don't see it right now, but there may be another way. Okay, now, what is F sub A? That's going to be an interesting question here. F sub A. And for that one, you have to look at the net force is equal to mass times the acceleration. Again, this is the net force. So in other words, if we draw it out graphically, we know going in one direction, we have the applied force. Opposing it is F sub k, and everything that's left over, that's the net force in the x direction. We'll just call it F sub n since we only have the x direction to deal with this time. And so looking at graphically, looking at what we could call a free body diagram, we would also have, if we drew the free body diagram, we would have the normal force going up, gravity going down. But this is all the forces in the x direction. And we know, and so what we can see from this is the net force is equal to F sub A going this way minus F sub k coming back. So in other words, we can solve this, the net force plus F sub k, that's equal to the applied force. In other words, the applied force has to overcome friction and then accelerate the mass by supplying that net force to it. And that's everything that's left over after it overcomes friction. So we can say we have F sub A is equal to mass times acceleration plus F sub k. Here the mass, we said, is 2 kilograms. The acceleration is given at 3. So we have F sub A is equal to 6 plus F sub k, that is plus mu sub k mg cosine of the angle. Again, this is just one for the reasons we've already talked about before. There's no slope. So we have mu sub k is 0.2. We have a mass of 2, and gravity is the fission of 10 here. So we have 4 again. So we have 6 plus 4. The applied force is 6 plus 4, also known as 10. So it's 10 newtons is the applied force. Part of it goes to overcome friction. The other part goes to accelerate the mass by giving it a net force. And there has to be a net force to accelerate the mass. Okay, so that's this question. What is F sub A? And now you can see why we had to solve the first 2 parts first, because now the third question, the energy of the applied force is F sub A times D. I could just, I mean, on the test, it's possible, I'll just say, okay, what is the energy that the applied force gives to the system? And then you have to realize that these first two steps are required to get there. So I'm not gonna necessarily prompt you with all those questions, but you see how to get there now, and you know that this is one that has a very good chance of being on the exam. Okay, F sub A, so now we just have, very easy to solve, times 13.5. So we have 135 joules. That's the energy of the applied force that it gives to the system. We know part of it's going to overcome friction, and part of it is accelerating the mass that is giving it kinetic energy. So we're going to have a way to check 4 and 5. 4, we're going to find the final kinetic energy and find the energy to overcome friction, and it's going to their sum's going to equal the applied energy. That's where it goes. It goes to overcome friction, and then to accelerate the mass up to its final velocity, which gives it mv squared over 2. Okay, so that's 3. So let's look at 4 now. Kinetic energy final is equal to what? Well, we know it's mv final squared over 2. So here's where, if you chose to go this route, well, it took longer to get the first answer, but you've already calculated the final velocity, so you save time on your second answer. You've already calculated VF as 9. So this is, from before it's 9, so we have 2 times 9 squared, and again, this is from earlier. We solved it, but again, it was V of t is equal to V0 plus AT, and so that was 0 plus 3t. So V of 3 is equal to 3 times 3, or 9. So that's...
Can we just catch up real fast?
What?
Can we just catch up?
Oh, yeah, I'm sorry. Okay, let me sit down here and I'll get a sip of water while you guys catch up with that. What's nice here too is that once we have the kinetic energy, we can get the energy to overcome friction in 2 ways that will double check each other as we get it. We know that the applied energy goes to kinetic energy and to friction, and so we can subtract the kinetic energy from the applied energy and get an answer. And we can also do F sub k times the distance, and we should get the same answer. So we have ways of double checking. Yeah.
I'm sorry, really quick, on number 4, with the MVF squared.
Right.
I know we got the VF from method 2.
Right, and then I put it again down here.
Yeah. Oh, okay, so if we didn't do, if we did
Right,
method 1, then
right,
X.
you would have to identify the velocity equation and then say, okay, 0 was the initial velocity, A was 3, that was given to us, and then just put in 3 into that equation, and you would get 9.
So either way, we had to end up doing method 2 in one point in time.
Yeah, you had to really, so which, I mean, method 2 will help you because you already have that at your disposal.
Okay.
It doesn't always work out that way. If I hadn't asked for that part, then you would have had extra steps you had to do, but.
It really comes down to if you ask for KEF and EF, method 2 should be the best way to go.
It looks like it, yeah.
Because I mean, by
Right,
okay.
right, because you're gonna have to do it at some point or the other.
Okay.
And if you wanted to do it both ways to double check, if somebody wanted to do that, if your answers don't agree, then you've made an algebraic mistake or you've misapplied the formula or something. Okay, so here the 2's cancel and we're left with 81 joules. And so we know that the applied energy, it goes, so we'll do this kinetic energy final and we'll box in the answer. But we know the energy goes to accelerate the object, that is to give it the kinetic energy, and it goes to overcome friction. It gives energy to overcome friction. So we can say one way of doing it is just 135 equal to 81 plus the energy to overcome friction, and we can do a subtraction, and we should get that is 54. Okay, joules is the energy to overcome friction. So that's one way of doing it. But let's do it the other way too, just to kind of corroborate the answer that we got. Okay, so we could do second method for the energy to overcome friction. We can say, okay, energy to overcome friction is equal to the force of kinetic friction times the distance. So that was, well, we calculated that before over here as 4. We know the distance is 13.5. And so that does give us exactly 54 joules. So we can see that we aren't just making a bunch of stuff and say, hey, this is how it works. Just trust me, this is how it works. It all does hold together. And if it wasn't consistent like this, then one or more of the equations would be wrong, or reality would be trying to trick us. Einstein said something about the process of discovering patterns and laws of nature, that reality is subtle, but it's not really malicious, so it's probably not going to do something malicious to us by giving us equations that suddenly become inconsistent at a moment's notice. Okay, so questions about this one? Again, we see that everything, the two approaches are equivalent, and it's good to have the two approaches because you can double check your answers to make sure that they're working okay. The last problem we're going to do is going to be similar to these, except that now we're going to look at an applied force to move an object up a slope. And that's going to be a little bit different.
You had also said you wanted to do the average power for this
Oh,
one.
I'm sorry, yeah, thank you. The average power. It's an idea I wanted to introduce here because power is going to come into play in a lot of other areas too. So the average power. Okay, we'll give a basic definition for power. We're going to modify maybe some later to make it more, to apply to more subtle situations. But really it's the energy over the time, it's the energy supplied over the time taken to supply that energy. So it's, I'm writing it out in long form here, or you can say it's the energy over the time, but just so we're clear on what energy it is.
Would the power question be on the test?
Yeah, it will be. I mean, it might be. It's one that's a candidate. And it's a really very simple calculation. Here, the energy that was supplied, that's the energy from the applied force. And the time taken, that was given as 3 seconds. So it really is just one more simple step after that. So we have 135 over 3, and that should be 45 joules per second. And that's also known as W for watts. So we have 45 joules per second, which is another thing for watts. And most frequently you'll see things referred to in terms of watts, how much energy per second is supplied to a system, often by electrical power sources, but other sources too. So you have energy in terms of joules per second or watts. Okay, so well, we're going to look more at power later. We're going to look at more in terms of a lot of different things to have to do with power, including the power that's given when an object radiates photons, aka light. We're going to look at equations that tell how much power is given at those times. Okay, so we've got one more example, and we have enough time to do it before we break for upstairs. If we get finished with the fourth example, we'll start looking at the 8 questions, the additional 8 questions. Okay, so question 4. It example seems like a funny word, X ample. It used to be ample, now it's not. Now it's scarcity. It's famine problem number 4. Okay, example 4. Okay, what I want to give is we're going to be going up a slope here. And so it's going to be the same type of a problem that we just did, except that without the time coming into play. We'll have 30 degrees again. And we'll have our mu sub k value of 0.2. That seems like a good value. We'll have our mass. We're going to have an applied force. It's going to have an acceleration that's constant the whole time. It'll again be 3 meters per second. And we're also going to say, I'm sorry? Oh, yeah, it should be per second squared. Well, let's make it to be completely just like it was before, except that now we're going to have it be going up a slope instead of not up a slope. So we'll have it identical in every way to what it was before. And our questions are going to be,
And the mass is going to be 2 kilograms, correct?
yeah, mass 2 kilograms. That's an easy mass to calculate with. I don't like to use 1 because 1 is so easy to get lost in the calculation, like it's not even there. But 2 reminds you that, hey, there's mass involved, and it's easy to calculate with too. Okay, so we're going to have the same questions. I'll write them out again because 1's going to be modified a little bit. Okay, so 1 is the distance that it travels as this thing goes up. We're also going to find out how high it goes up the slope when compared to the ground. That's going to become important. Then we're going to calculate the applied force and the energy supplied by that applied force. Then we're going to calculate the kinetic energy final, the potential energy final. That's going to come into play here too, and the energy to overcome friction. And again, we'll use we'll calculate the power, and that's what we're going to do with this. So all these are going to be things that we calculate. The final potential energy, we're going to count H is 0 here, and so this is our delta H. In other words, we're going to look at this as H final. That's going to be, but we're going to count the ground as being 0 potential energy. We should also specify this thing's not moving at the start. So again, most everything, a lot of the things proceed as from before, but let's kind of quickly run through it again. Again, we have an x of t equation that just looks like 3 halves p squared. We did the derivation for it before. It goes for 3 seconds, so it goes 13.5. All that's things that we did previously. Now the height, that's going to come in handy later, because we're going to show 2 ways of solving for this potential energy final. Yeah.
Now, again, since you're asking for the PEF and the KEF, we should be doing method 2, correct? The V of t squared, or V of s squared 1?
Oh, yeah, yeah, we could do it that way too. It's easy to find the other way too, but, okay, so H, let's get H. Now we know that it's gone up 13.5, and we know the angle is 30 degrees, and this distance, that's H final. So we know that that's the opposite, so we have the sine of 30 degrees is equal to the opposite over the hypotenuse. So we have 13.5 sine of 30 degrees is HF. So finally we have, what is this? That's, 6.75? Because this should be 1/2, and that should be 6.75 meters. That's the final height. And again, we're calculating this right now. I might not prompt you to do that later, but it's going to help us with one of the methods of solving for the final potential energy. Okay, so we have the first part. Are there questions about that first